So welcome to the Lab 5 preview. So this is the last, well, this is technically the last lab if you are not aiming for an A+, but if you want to get an A, you definitely don't want to miss this lab. So give you some heads up. So first of all, where are we coming from? So except for the lab 1, that's only like a practice of the tools. Starting from lab 2, we are gradually building up the processor. So in lab 2, you are having a processor that only has the data path elements, and it doesn't really do anything. So instead of running a real program, you have to do unit test. However, in lab 3, we start to add support to some set of instructions that does not include branch and jump instruction. So that's lab 3. And now in lab 4, a lot of you are probably struggling with. We are trying to add support for branches, jumps, and some more exotic flavors of low store instructions. And if you are still not clear about like what's each instruction about, I believe the write up, oh sorry, the lab web the page for lab 4 contains very clear definition about what the additional instruction is about and what value to set in each of the control unit. So don't be lazy, just go through the detail and you will find out it's not that hard. But one thing I do want to remind you is that, well, some of the instruction, instead of using sign extended, you have to use 0 extended. For the data memory, if you just give the size in, it just give you the byte of memory. But depends on what instruction you are using, you have to shift it to the right place. So this is the difficult part of lab 4. So for lab 5, the only thing that you need, well, the only goal of lab 5 is that we want to pipeline it. We want to pipeline it, as you can see here, right? You want to pipeline it. So previously we have learned if you want to pipeline a processor, this is what you need to do. Like you add pipeline registers. However, is that simple, right? What's wrong with this pipeline is that if you look at the write rec 1, right? You get your data from the write back stage. That part is correct. However, the write rec is actually the instruction that's currently in the instruction decode stage. So in addition to that, this is what you have to modify, right? You have to make sure that, well, instead of using the write rec of my current decoding instruction, you have to propagate that throughout the pipeline register and use the one that's coming from your write back stage. So that's part of the modification that you need. Is that everything? The answer is definitely no, because previously you have learned for pipeline processors, we have to address the pipeline hazards. And there are 3 types of hazards: the structural hazard, the control hazard, and the data hazard. And the structural hazard means that we have hardware limitation that doesn't support simultaneous execution of instructions. And presumably, if you design the processor properly, you shouldn't meet the issue. And another type of hazard is control hazard. So whenever you have a branch, you are going to have a control hazard. And the last type is called data hazard. Is an instruction depending on the output of another instruction. So through the 141 class, you should already learn that here are the solutions to 3 different types of pipeline hazards. So structural hazards, and if you look at the solutions carefully, stalls is the only type of hazards. It's the only type of hazard that's the only technique that applies to all 3 different types of hazards. And as you could imagine, the stall is just slow. It's slow, but it will work. It will work, right? So, but for compiler, it doesn't work for CSE141L because in this class we just give you the binary. So there's no way you can modify the compiler to make it work. So structural hazard doesn't work, and it doesn't work out if you use the compiler solution. And hardware optimization, in case your register file is designed properly, it shouldn't be a structural hazard. in your write back stage. However, if you didn't revise your register file design, and then there might be some sort of structural hazard you have to deal with it. And so presumably but the thing is, like, if you feel like if you are lazy about redesigning your register file because you don't know if that's going to make it work or not, then you can think about like adding a stall as well. And for control hazard, stall is definitely something going to work. And another thing that you can potentially think is like the textbook, they move the branch resolution to the instruction decode stage. But the cost of doing that is that, well, you will spend more time in instruction decode. And another solution is branch prediction. So as you learned in our class, you can statically predict taken or not taken. If you want to predict taken, you need a branch target buffer. If you predict not taken, if it's a loop, then you are not probably going to win anything. However, if it's a straightforward branch, you are going to save a few cycles, right? However, if you predict incorrectly, you need to flush instructions, and the flush is not, it would take you some time to figure out how to implement that. However, high risk, high reward. So in this class, if you implement a branch prediction, you will get an A+. However, the risk is that if you didn't get it right, your processor is not going to work. So it means that your left 5 is not complete. So it will give you an A-. And for data hazard, stall again would work. Data forwarding is the best solution. However, again, if it doesn't work, it will get A-. But if it does work, you will get an A+. So right now, it's you and your group's decision to see what you want to do. However, the safest way to do is always like having a stall. And even though you do data forwarding, there are still cases that you have to stall. So let's look at how stall works in detail. So for control hazard, I don't think we have to go through the first 3 cycles, cycle by cycle. So now I fetch a branch instruction, and through some kind of logic, I can probably tell this is a branch instruction by looking at the instruction code. So when I'm decoding, if I know this is a branch instruction, I know the currently fetched instruction is not going to be trustworthy because it might get from the wrong PC. So instead of getting the output from what you are reading from, you should make this instruction a no-op instruction. So you should just put a 0. You should just zero out your pipeline so that the output of instruction fetch stage will be no-op. And with the no-op instruction, the next cycle, when a branch is still resolving itself, the add instruction, well, we'll go to the no-op instruction will go to decode. But don't worry, since we are updating register 0, there's nothing else we need to worry about. And in the meantime, when you are fetching, just ignore what you fetch and set it to no ops as what we did in the last cycle. So now the next cycle, when a branch is resolved, we know we are going to take sub. Just resume the PC at the right place and refetch this instruction as what you find out here. So that would be the right way of handling the branch control hazard. And as you can see, the basic idea of stall is inserting no ops. Now, let's look at the data hazard. So for data hazard, it's also the same that, well, let's say like this pair of instruction, we know if you have an add instruction immediately following a load, if they depend on the same register, then there's going to be a data hazard, right? And but for this particular instruction, right, we know the load instruction can only generate its outcome after the memory stage. So because when the load instruction is in the memory stage, we know the add instruction is not going to receive its correct value anyway. So we just force the add instruction to stay at the same stage. And again, because the add instruction stays at instruction decode, so the sub instruction cannot be advanced. So in this way, your PC has to stay at the same instruction. And but in the meantime, the execution stage, you want to insert a no up, zero out your register, pipeline register, to make sure that the sum of the random value that's in your circuit won't affect your correct result. So this is important, that you want to insert no up whenever it's appropriate. So that's so after you insert that no up, and after the load instruction finishes memory stage, you can just do as usual, right? So if you look at the whole idea of stall, it's just like, okay, we disable the update of the PC, and in the meantime, we insert no ops whenever it's appropriate. So so for control hazard, right? How to implement a stall, right? You just need to make the instruction fetch and decode stage output zeros. And for data hazard, without data forwarding, then you have to stall, and whenever an input is an output of a later stage. So you have to refetch the same instruction. You have to decode the same instruction, so that the time when the time the value is propagated, you will get the right value. And finally, you have to zero out the IDEX pipeline register, because if you are fetching a value when the value is not ready, those values are not trustworthy. So when you say zero out, it's technically inserting no ops. So if you want to implement the stall, you need a hazard detection unit like this, which it will go through all the outputs for previous instructions, and compare it with the input of my current instruction to see if there is any match. And also, some instruction, they have two inputs. Some of the instruction have only one input. And how do you know this? You have to check what type of instruction it is. And for those instruction with data hazard, you want to insert no up here. And for those instructions, you have the control hazard. You want to insert no ops here. So that's why we have this different parts of the circuit to implement your control, your hazard detection. All right. So what I want to say is that some of you will feel like, okay, implementing 5-stage pipelines is too complicated. So here I provide you some alternative ways of alternative design for a pipeline, and they are all valid. And if you implement any of this, then it still counts as a Lab 5 valid submission. So the option here is 4-stage pipeline. And example is like IFID, and you have a joined EX plus MEM and write back. And you know, because you have the EX plus MEM, and MEM is already the critical path. So this is not going to be very efficient, but should be better than a single cycle processor. 3-stage pipeline, you could do whatever you want. And with like IF plus ID, right? And EX plus MEM or write back, right? So this would be an example way of making it 3-stage. And for 2-stage, the only available option is like you combine the IF and ID together as stage and the rest of another stage. And there is a specific reason we want to do that, because we want to make sure that you understand what's going on for data hazard and control hazard. And if you leave the instruction fetch alone, but with the rest, this is not possible. This is possible, but it's not fulfilling our educational purpose. So I want that to happen. So if you try to do a pipeline with IF and the rest stage, that's not allowed. So this is the potential ways that you could do. And for benchmark, we just use the same benchmark as you had in the previous lab. So so there's no new surprise of the code, and it just make your processor pipelining. And we have some test scripts that you can try and see if that makes your life easier. Okay, regarding interview questions. First of all, again, show us the schematics and show us the waveform of the 3 benchmark until the end, so we know it's working. Measure the instruction count, the total cycles, the CPI and report your maximum frequency. And the reason is because we want to calculate the performance of a processor, and we will give awards to those who achieve the best performance. In addition, if you really want to get an A+, here are some ideas. So previously we mentioned you can implement data forwarding, you can implement branch prediction. And today in the lecture, you learn cache. So if you know how to do memory, if you know how to do how to implement SRAM using FPGA, you can do it. Superscalar, meaning that you have dual pipeline, that's also an option. And we have spatial bonus for your fastest processor. By the way, if your processor is the fastest among the class, even though you don't have data forwarding, you don't have prediction, you are still going to get an A+. So definitely worth a while for you to tune up your performance, because if you have the best performance, you are going to get reward, you are going to get an award, you are rewarding for a better grade. So definitely, even though you are not thinking about optimizing for pipeline structure, you should think about other potential ways. All right. Finally, if you don't have any other question, the Lab 4 will do Friday before 5 p.m. interview with any of us. Any of us meaning that like the professor also counts. And Lab 5 and Lab C, we will extend the deadline to September 6th. However, there's no further extension afterwards. So if you cannot find any of us before September 6th, 1 p.m., we are not going to give you any more demo, because we have our deadline of submitting your final grades. And this is also the last CSE141L lecture, and we don't have CSE141 lecture next week, and we don't have any more CSE141L lecture anymore. It's all about the tutor hours, the TA hour, the office hours by me. Other than that, if you don't have any question, I would wish you enjoy the rest of the day. Goodbye.